Okay, let's talk about simplifying assumptions one more time. If Ka is small and the initial concentrations are large, the change to the initial concentration of Ka may usually be neglected. It's going to be neglected in the problems that I give you on exams and quizzes. So hydrogen ion due to the autoionization of water, we talked a little bit about that. Kw can usually be neglected unless the hydrogen ion concentration is close to 10 to the minus 7 molar. We're going to go ahead and neglect it. All right, so let's take a look at percent ionization. Percent ionization, I know I've done this as the anion, but essentially once you've calculated X, and just take X, divide it by the initial concentration of your weak acid, multiply by 100, and that's going to give you the percent ionization that you're after. So whatever X is, solve for it. Divide by HA. Now, and then multiply by 100. Now, we'll use the 5% rule as long as the percent ionization is less than 5%. Now, it's going to be less than 5% in the problems that I've given you, but I may ask you to calculate the percent ionization. So you just need to remember that percent ionization is going to be equal to X divided by the concentration. In this case, acid, it could be the percent ionization of base. It would be the same thing, X over whatever the weak base concentration was times 100 would give you the percent ionization as well. Okay, so let's go ahead and let's work another problem. Okay, let's work this problem. Now, here's the deal. We're going to calculate the percent ionization of the 0.15 molar acetic acid in the previous problem that we worked for our weak acid, and we're going to compare that to the percent ionization of a tenfold dilution acetic acid. Now, for the original problem that we calculated the hydrogen ion concentration, the hydrogen ion concentration was equal to 1.64 times 10 to the minus 3. Just refer to the previous video. And so let's go ahead and let's calculate that percent ionization. That's 1.64 times 10 to the minus 3 divided by the original concentration of the acid, which was 0.15 molar, and then we'll multiply times 100. And when I solve for that, I get 1.09%. Okay, so that's the percent ionization for the first problem in calculating the pH of a weak acid. That was the percent ionization, well within the boundaries of being less than 5%. So here we go. We want to go ahead and we want to calculate the percent ionization for an acid that has a tenfold dilution. Same acid, it's still acetic acid. It's still got a Ka of 1.8 times 10 to the minus 5. Here's our ICE table, ICE. This now, instead of being 0.15, is 0.015 molar. It is a tenfold dilution. We just basically divided this by 10. All right, and we wound up with a tenfold dilution. This is 0, this is 0, this is minus X plus X plus X, and then 0.015 minus X, X, and X. We're going to do exactly the same thing we did in the last problem. X, which happens to equal the hydrogen ion concentration is, we are assuming that this X is small enough to ignore. We're going to, since we're calculating the percent ionization, we'll find out. I'll go ahead and set up the equilibrium constant expression. Ka is equal to H plus times A minus divided by the weak acid concentration. And again, we're going to ignore that X. And so we solve for the H plus concentration, and the H plus concentration is simply going to be equal to the square root of the Ka times the initial concentration of our weak acid. So we'll go ahead and plug that in here. So the Ka is 1.8 times 10 to the minus 5. Our concentration of our acid this time is 0.015 molar. And let's see what we get. This time we get, looks like 5.20 times 10 to the minus 4 molar. It's a lower concentration than we got in the original concentration with the 10 times more concentrated solution, and that made sense based on Le Chatelier's principle. We had a higher concentration of reactants, so we have a higher concentration. However, let's take a look at the percent ionization. The percent ionization is going to be 5.20 times 10 to the minus 4 divided by 0.015 times 100. When I finish that calculation, I get 3.46% ionized. So if I compare the percent ionization for the more dilute concentration, I see that my percent ionization has increased in spite of the fact that my hydrogen ion concentration has decreased. Here's a way to think about this. As we lower the concentration of our reactant over here, here's what's happening. Think of it from a Le Chatelier's point of view, where if this were a gas phase reaction, and what I'm doing by diluting the solution is I'm making the container larger. And so the equilibrium shifts toward the side that has more moles. So we have 2 moles over here on the product side. We only have 1 mole over here on the reactant side. And so because there's more room, because the solution is more dilute, the dissociation increases in spite of the fact that the concentration of my reactant decreases. And that's just a way to think about this particular effect. So the effect is, as the weak acid becomes more dilute, the percent ionization, it goes up. So that's the effect. When weak acids or bases are diluted, the percent ionization actually increases. So if we had 0.1 molar concentration of propionic acid, it'd work this problem. We had a 1.1% ionized. I diluted it by a factor of 10, and the percent ionization went up to 3.6% ionized. So as the concentration of weak acids and weak bases are diluted, the percent ionization increases. Something to remember.